Hello and welcome to Probability and Statistics for Business and Data Science. I'm Jose Portilla and I've taught over 600,000 students here on Udemy in a variety of topics, including Python, data science, machine learning, web development, and more. I've also conducted corporate training at some of the world's largest companies, and I'm super excited to bring you my exclusive training on probability and statistics, with a focus on business applications and data science. Let's take a look inside the course. We'll start by talking about the basics of data, understanding how to examine it with measurements of central tendency, dispersion, and also building an understanding of how bivariate data sources can relate to each other. Afterwards, we'll dive into probability, learning about combinations and permutations, as well as conditional probability and how to apply Bayes' theorem. Then we'll move on to discussing the most common distributions found in statistics, creating a solid understanding of how to work with uniform, binomial, Poisson, and normal distributions. After that, we'll talk about statistics, applying what we've learned so far to real-world business cases, including hypothesis testing and the student's t-distribution. We'll end the course with 3 sections on advanced topics, such as ANOVA, analysis of variance, understanding regression analysis, and finally performing chi-squared analysis. The sections are modular and organized by topic, so you can reference what you need and jump right in. Each section includes a full assessment as well as quizzes to test your understanding and new skills as you learn. The course includes clear HD videos, external resources, built-in quizzes, and explanatory slides for all the concepts. Not only do you get great technical content, but you'll also have access to our online Q&A forums as well as our student chat channel, where the teaching assistants and myself are happy to help out with any questions you encounter. Upon finishing this course, you'll receive a certificate of completion that you can post to your LinkedIn profile to show off to your colleagues or even potential employers. All of this content comes with a 30-day money-back guarantee, so you can try out the course risk-free. So what are you waiting for? Become a pro in probability and statistics. Enroll today, and we'll see you inside the course. Hello everyone, and welcome to this course overview lecture. I have one quick favor to ask of you, is that you please don't skip this lecture. We're going to discuss the best way to take the course, as well as where you can find the course notes. We're going to keep things brief, that way you're not stuck here for a long time, but let's go ahead and get going. So first off, welcome to the course. Thank you so much for enrolling. In this lecture, we're just going to get some useful tips for going through the course, how to get help during the course, just a little bit of advice on how to approach the course, where to find the course notes, and then how to use the student chat channel. As far as useful tips go, you can use the video player setting to speed up or slow down videos. So as you're watching a video, if you hover your mouse over the bottom of the video, you'll see a toolbar show up. And currently on the left-hand side, you'll see a 1x. And if you can click on that, adjust the speed. There's also a gear setting. So if things don't appear at the highest quality, you can click that gear setting and raise it up to 720p or 1080p for higher streaming quality. You can also use the Udemy app to download videos of the course lectures. Also, please make sure to use the Q&A forums. There's lots of discussion available there for you to check out. Let's say you're stuck during the course on a specific course question or on a specific course lecture. The best ways to get help, usually a quick Google search will actually answer your question faster than anyone can, just because a lot of these statistics questions, they've already been around for a long time. So a quick Google search of what you're looking for may actually be the fastest solution. If not, and it's more specific to the actual course lecture, you may want to do a quick search in the Q&A forums in the course because other students may have already posted a question and solution to what you're looking for. If you still can't find it, go ahead and check out the resource links that are attached to most of the lectures for additional information. And you can also check out the FAQ lecture for basic questions, such as where to find the notes or questions on Udemy certification. Now, let's say none of those solutions have worked for you so far. No worries, all you need to do is submit a new question to the Q&A forums. Please include as much detail as possible on what you've tried, and also please include a screenshot. As far as a quick note on getting help, please keep in mind that we cannot help with personal homework assignments outside of the course in the Q&A forums inside the course. If you're maybe working on a homework assignment at school that's unrelated to the course lectures, a great place to post questions on that would be to reach out for help on the Discord chat channel. That's really what that Discord chat channel here is for. The Q&A forums, they're really just for us to help you with stuff related to the course and the course material. Now, if you're having issues at a platform level, things like video playback issues or audio issues, certification issues or payment issues, we actually don't handle that. Udemy does. So all you need to do is email support@udemy.com, give them details of your platform related issue, and they'll be happy to help you out, and they'll get back to you as soon as possible. Now, as far as the best way to approach the course, I personally think the best way to approach the course is to start by reviewing the actual video overview of whatever topic you're looking at. Essentially, just watch the video lecture. And then after you're done viewing it, for a lot of the lectures, you'll notice a little blue icon pop up saying there's resources attached to the lecture. Those are just external links that will help you out, and will also talk more about the specific probability or statistics topic that we included in the video. So my recommendation is you watch the video overview, and then if you're still a little fuzzy on things, go ahead and check out those external links. As far as getting the course notes are available as a downloadable .zip file in the FAQ lecture as a resource. So in the very next lecture, it's an FAQ, it's an article lecture. You'll see a little resource thing pop up, and all you need to do is download that zip file, unzip it, and you'll have PDFs of everything we covered during the course. Now, that student chat channel I mentioned earlier, that Discord chat channel, you can use the link in the automated welcome message to join our Discord server. The automated welcome message also includes a link to a YouTube video describing how to use and log into the chat server. That Discord chat channel, it's also linked in the FAQ lecture in case you don't want to go back and see your autumn welcome message here on Udemy. So you can find it there as well. Now remember, the purpose of the chat channel is to connect with students with other students. If you have technical questions, again, related to the course material, that's best suited for the Q&A forums. As far as the course curriculum is concerned, these are the main topics we cover during the course. We talk about data, probability, distributions, statistics, then we move on to advanced topics like ANOVA, regression, and chi-squared analysis. Keep in mind that this course actually has a very gradual start, specifically in the data and probability sections. We take it very slowly because we're not going to assume that you know anything. But if you've already taken some probability or some math, or maybe you already have some familiarity with these topics, you may actually want to skip ahead to the end of section assessment first to kind of gauge your skill level, and maybe you don't want to view the first couple of sections. So it's really up to you depending on what your previous experience is. So keep that in mind. The course is very modular, so you can jump around however you please. Okay, well, that's all I have to say for the course overview lecture. And finally, thank you so much for enrolling in the course. Feel free to message me here on Udemy if you have any questions, or if you have technical questions related to the course content, feel free to post to the Q&A forums. All right, we'll see you at the next lecture. Welcome back, everyone. In this lecture, we're going to be talking about the binomial distribution. Specifically, we'll see some examples of a discrete binomial distribution. So let's first talk about what the term binomial actually means. Binomial means that there are two discrete, mutually exclusive outcomes of a trial. So what do we mean by that? Well, remember bi, that term just means two, like a bicycle has two wheels. So when we're talking about binomial distributions, we're talking about things with two discrete outcomes. So something like heads or tails, on or off, sick or healthy. And often in statistics textbooks, this is known as success or failure. And experiments or trials that follow this sort of behavior actually have their own terms. So these are called Bernoulli trials. So what we mean by that is a Bernoulli trial is a random experiment in which there are only two possible outcomes, success or failure. And there are two key things that have to happen in order for something to be labeled as a Bernoulli trial. So let's imagine that we're going to have a series of trials, n, so n number of trials, and we want it to follow a binary distribution. So it will follow that so long as two key things are met. One is that the probability of success p is constant, and b, the trials are independent of one another. So what do we actually mean by that? Well, let's take a look at the first one. The probability of success p is constant. If you end up deciding that you're going to flip a coin and treat that as a Bernoulli trial, then you could say that flipping a heads is a success and flipping a tails is a failure. So you can easily, with context, categorize any binomial outcome as success or failure. You just have to choose one of them to be a success and the other one to be a failure. So let's go back to that example. We're flipping a coin, and if we flip heads, we get success. So let's see if that meets the first term. The probability of success p is constant. Well, if you have a fair coin, then the probability of flipping a heads is going to be constant. It's going to be 0.5 no matter what, because you have a fair coin. So that condition is met. Then for condition B, the trials are independent of one another. This one's really critical. That means that these are independent events, which makes sense. If we're flipping a coin, the previous coin flips have no effect on the future coin flips if it's a fair coin. So that condition is also met. So if you meet these two conditions, then you have a Bernoulli trial. So let's take a look at the binomial probability mass function. And we actually plotted out a mass function for the uniform distribution earlier. Now we're just going to do one for a binomial probability. So this gives the probability of observing X number of successes in N number of trials. So the probability of success on a single trial is denoted by P. And this assumes that P is then fixed for all trials. And then we actually get this equation. So we're going to talk about this equation and how to actually read the syntax in just a little bit, but I want to go over these 3 bullet points in a little more detail. So again, what this equation does is it gives you the probability of observing X number of successes in N number of trials. So again, if we go back to that coin flip example, we could say that we want to see the probability of flipping 3 heads in 10 coin flips. So N would be 10 coin flips, X would be 3 heads because we labeled that as success. Then the probability of success on a single trial is denoted by P. So that would be 0.5 because the probability of flipping heads on a single trial is 0.5. And then we assume that P is fixed for all trials. So it doesn't matter how many times I flip that coin, that P is equal to 0.5 isn't going to change. What I want to do is show you an intuition of what the actual binomial distribution would look like if you were to plot it out. And we're going to walk through 2 examples. One is for an experiment where you label flipping a heads a success and flipping a tails a failure. So that means your probability of success will be 1/2, and then we can play around with N number of trials, and then we get a distribution for how many successes we're likely to get and what's the probability of that. And then after that, we're going to show you an example with a fair 6-sided die. So what that means is you label one of the numbers as a success, so rolling 1 is deemed a success, and then rolling any other number is deemed as a failure. So then we can play around with the probabilities there, and then also play around with how many actual trials we do. And then we can see how that affects the binomial distribution. Let's take a look in this in an application. Okay, here I am at my actual application, and I want to break down what this visualization is actually showing. It's showing the binomial distribution for some N number of trials with some P probability of success. So that means I can adjust the number of trials I perform. So if I'm thinking about flipping a coin, I can flip 53 coins, 54 coins, 55 coins, etc. And then I can adjust P. So right now I have it on 1/2 because it's a fair coin. And I say something like the probability P of flipping a success or heads is equal to 1/2. But for other things, I could adjust it to 3/5, 2/3, 1/6, and so on. So let's keep it to 1/2. So we keep this example of flipping a coin. And I'm going to set N equal to, right now, 50. So now let me explain what this y-axis and what this x-axis actually represents. So the y-axis is just the probability. And then the x-axis is the number of successes. So what does that actually mean? Well, it means as I hover over these bars, if I flip a coin 50 times, then I have a probability of, here at the top of this bar, we can see its height is 0.107 or 0.108 more or less, and I have that probability of getting 24 successes. So that means I have a higher probability of getting 25 successes, and then a lower probability of 26, and so on. So it makes sense, since I'm flipping a fair coin, that my highest probability is that I hit 25 heads or 25 successes. And notice then it starts to adjust as you get further and further away. So as I get closer and closer to a lower number, I have a very small value of only flipping that many heads. And if I go higher and higher, then I also get very small values of flipping mostly heads. So it should more or less be about half, which is why we see the distribution hovering around 25. So let's take this to the extreme. Let's lower the number of trials to just 1 trial, a single flip of a coin. It makes sense now that I can see the chance of 0 successes and the chance of 1 success. And notice it's discrete. There's nothing in between those values of 0 and 1. So what that essentially means is as I hover over this, we can see here on the y-axis, it's 0.5. So that means I have 0.5 probability of 0 successes, essentially flipping a tails, and I have 0.5 probability of 1 success, flipping a heads, which makes sense because I'm doing this for a single coin flip. And as I increase this to now 2 coin flips, now I can see my probabilities change. I have 0.25 probability of 0 successes, 0.5 probability of 1 success, and 0.25 probability of 2 successes. So this is flipping 2 tails, flipping 1 head and 1 tail, or 1 tail and 1 head, and then flipping 2 heads. So we can begin to play around with this and see how the distribution starts to align itself for different probabilities and different number of trials. So now finally, let's go through a theoretical example of rolling a specific number from a fair-sided die a specific number of times. So I wanted to see what were the odds of rolling a 4 10 times if I rolled the dice 50 times. So we can calculate that easily. All we end up doing is we set the number of rolls. So let's say I'm going to roll something, let's say I'll roll a fair die 50 times. The probability of rolling a 4 off a dice any one time is 1/6, and then I can see the actual probability of rolling that many number of successes, or rolling any particular number that many times. So the highest probability I have right now is 8. So I have the highest likelihood of rolling a specific number off a die, such as a 4, 8 times, and that probability is 0.15. And then it gets a little less, and as it keeps going closer and closer to the n number of trials, the probability becomes super, super small. Which makes sense. You have an extremely low probability if you were to roll a die 50 times that you would get the same number each and every time out of those rolls. Just like you have the same very low probability of never rolling that number. Keep in mind, it's still possible, so notice none of these are actually truly 0. They're just very, very, very small numbers. Almost 0, but not truly 0. Okay. So that's the binomial distribution, and you can check it out here on this little application. Let's continue on with the rest of the slides. Okay, so let's actually now use this equation, expand it out, and go through a quick little exercise so you can see an application of the binomial distribution. So again, we went through these two examples of a fair-sided coin and a fair-sided die, and now we'll do a little exercise. So let's imagine you're going to roll a die 16 times. What is the probability that a 5 comes up 3 times? So based on the chart, if you were just to put that on the chart, it would be just shy of 0.25. But we can actually use the equation to figure out that exact value. So we're going to fill in x is equal to 3 because that's the number of successes we're looking for. N is equal to 16. That's the number of trials. We're rolling that die 16 times. And we know the probability of a success, the probability of rolling a phi is 1/6. So we take those numbers, and then we take our equation and plug them in. Now, there's a shorthand notation we haven't seen before, which is that first term, that parentheses n over x. That's actually just a combination. So that expands out to look something like this. That's essentially just shorthand for that full combination formula, which is n factorial divided by x factorial minus times n minus x factorial. And then we take the successive probability of success, take that to the exponent of x, and then multiply that by 1 minus p to the exponent of n minus x. So you take all the numbers, plug those all in, you get something that looks like this. You take out your calculator, and then you end up seeing that it's equal to 0.242. As we saw in that chart, a little shy of 0.25. Now keep in mind, while you can technically do this all by hand, typically you can just pull out a formula in Excel or even use a programming language such as Python to do this automatically. So if you're using Excel, the way you would use that is you would call the binom.dist function, and then you would pass in the numbers in this order, 3, 16, 1, 6, and then you would set up false, and that would return back 0.242. And you can check out the Excel documentation for other parameters you can pass in. If you happen to be using a programming language such as Python, you can use a library called scipy. You say from scipy.stats import binom for binomial, and then we call binomial.pmf for probability mass function, and then again you pass in those numbers in the same order. 3, which is the actual number of successes you're looking for, and the number of trials, 16, and then 1/6 is the probability. And then that gets you back the same result. Keep in mind, if you don't have Excel or if you don't have Python, you can just Google search for binomial distribution calculator, and there's tons of websites that already have that ready to go. In case you find yourself needing a quick little fix, just open up your browser, Google binomial calculator, and you should find what you're looking for. All right, so that's it for the binomial distribution. We'll see you in the next lecture where we continue our discussion of discrete distributions. Welcome back, everyone. Now it's time to actually put our understanding of hypothesis testing to a real-world example. So we're going to start off with exercise number 1. And for this next example, we'll work in the left-hand side of the probability distribution with negative z-scores. So keep that in mind because later on, we're going to be looking things up in a z-table. Then we'll show how to run the hypothesis test using the traditional method. Afterwards, we'll show you how to do it with the p-value method. So let's imagine this situation. A company is looking to improve their website performance because they think the load times are too long. Currently, pages have a mean load time of 3.125 seconds, with a standard deviation of 0.7 seconds. So they hire an outside consulting firm to help fix the code and improve the load times. Management decides they want a 99% confidence level that the mean load time actually improved. So we do a sample run of 40 of the new pages that the consulting firm helped fix, and that has a mean load time of 2.875. So the average of this sample run of 40 has a lower load time. But then the question is, are these results statistically faster than before? Because remember, there was a standard deviation of 0.7 before the consulting firm even came in. So with this sample run of 40, we want to know, is that mean load time that's shorter, 2.875, is that actually statistically faster than before? So that's why we need to use hypothesis testing in order to answer that question. So we have a couple of main steps to do. The first one is to state the null hypothesis. So our null hypothesis is that the average load time is going to be greater than or equal to 3.125. The alternative hypothesis is going to be that the average load time is less than 3.125. Then we set a level of significance. In this particular example problem, it was management that mandated an alpha value of 0.01 because they wanted to be a 99% confidence level. So 100 minus, or 1 minus 0.99, that's equal to 0.01. Now, if you weren't mandated some sort of level of significance, then by default, the convention is to say 0.05. So keep that in mind. If you see a problem like this and they don't actually tell you what the level of significance is, you can just default to alpha is equal to 0.05. Then we need to determine the test type. In this case, we have the left tail, right tail, and two tail options. But recall that we're saying the null hypothesis was that the mean is greater than or equal to, which means the alternative hypothesis is then less than. So that means we're going to be using the left tail test type here. So we'll start off with the traditional method. We have all our variables ready to go. So what we're going to do is calculate the test statistic. So in this case, using what we already know, we can calculate z is equal to negative 2.259. And now we also have to decide what the critical value is. So what we end up doing is we do a z-table lookup on our alpha value. So that alpha value was on 0.01. So now we have our test statistic, that capital Z, negative 2.259, and the result of our z-table lookup on 0.01, which is, we state lowercase z is equal to negative 2.325. So what we end up doing is we fail to reject the null hypothesis. Since negative 2.259 is still greater than negative 2.325, the test statistic falls outside the rejection region. So we can't actually say that the new web pages are statistically faster. Now let's imagine you wanted to take the p-value approach. In that case, you still calculate the test statistic, negative 2.259, and then your p-value, you actually do the z-table lookup on negative 2.26, or as close as you can to negative 2.259. So you look it up through a z-table on your test statistic, and then you look up what the p-value that corresponds with that is. So that ends up equaling to 0.0119. So with the p-value method, again, you fail to reject the null hypothesis because 0.0119 is greater than 0.01. So that's greater than the level of significance. Notice it's pretty much the same thing, as you're just going about it the other way around. With the traditional method, if we come back here, with the traditional method, you are looking up that critical value based on the confidence level. In the p-value method, you were basically doing the reverse. You were looking up based on the test statistic you solved, grabbing that p-value and then comparing it to your confidence level. And you still do the comparison the same way. And in this case, again, you fail to reject the null hypothesis. So two different approaches that get you the same result. And again, overall, we cannot say that the new web pages are statistically faster. Okay, that was a quick example of hypothesis testing for the mean. Now, coming up next, we're going to show you testing for proportions. We'll see you there.